In this video, we're going to look at a few more examples of finding limits of sequences. Part A, an is equal to 1 plus negative 1 to the n times root n divided by 2 to the n for n larger or equal to 1. Part B, bn is equal to log of sine of 1 over n plus log of n for n larger or equal to 1. Let's look at part A. For part A, we have an is equal to 1 plus negative 1 to the n times root n divided by 2 to the n. Let's compute a few terms. So let's put n equals 1. A1 is equal to, we're going to get 1 plus negative 1 to the power of 1 is negative 1. So 1 plus negative 1 times root 1 divided by 2 to the 1, we're going to get 0. In fact, all the odd terms will be 0. Let's look at A2 is equal to 1 plus negative 1 squared is plus 1 times root 2 divided by 2 squared is 4. So we get 2 root 2 divided by 4, and we get root 2 divided by 2. A3 will be 0 because we get 1 plus negative 1. Negative 1 raised to an odd power will always be 0. And let's look at A4. A4 comes out to 2 times root 4 divided by 2 to the 4, which is 16, and simplifies to 1/4. A5 is equal to 0. Intuitively, we can kind of see how this converges because all the odd terms are always going to be 0, but the even terms are progressively getting smaller and seem to be approaching 0, but we have to prove that. So it's clear that when n is an odd integer, an is equal to 1 plus negative 1 to the n times root n divided by 2 to the n is equal to 0 when n is odd. And the reason, of course, is 1 plus negative 1 to the n will always be equal to 0 when n is odd. And when n is an even integer, we get an is equal to 1 plus minus 1 to the n times root n divided by 2 to the n. But this part is going to be 1 plus 1 because negative 1 raised to an even integer will be plus 1. So we'll always have 2 root n divided by 2 to the n. So when n is odd, n is equal to 0. And when n is even, an is equal to 2 root n divided by 2 to the n. So it's logical to try to apply the squeeze law to find a limit of an. So the sequence is 1 plus negative 1 to the n times root n divided by 2 to the power of n is less than or equal to 2 root n divided by 2 to the n. So even integers essentially produce the upper bound for the sequence, and odd integers always produce 0 for the sequence, so that produces a lower bound, which is 0. Now taking a limit as n goes to infinity of every term, limit as n goes to infinity of the middle expression, and limit as n goes to infinity of the right-hand expression. All right, this part is definitely 0. Intuitively, we can see that this will be 0. Why is that? Well, 2 root n is not going to grow very fast. That's a root function. 2 to the power of n in the denominator is an exponential function, grows much faster than the numerator, and hence the ratio will approach 0 as n becomes increasingly large. But we have to verify that formally. So let's consider the limit as n goes to infinity of 2 root n divided by 2 to the n. Now you will notice that 2 root n approaches infinity as n goes to infinity. 2 to the power of n also approaches infinity as n goes to infinity. So we have the infinity divided by infinity pattern. That means we should apply L'Hopital's rule to compute the limit. So we're going to apply L'Hopital's. Limit as n goes to infinity, 2 root n divided by 2 to the n is equal to, by L'Hopital's rule, we take the derivative of the numerator, and divide by the derivative of the denominator, and take the limit. So what is the derivative of 2 root n? That's going to be 2 times 1 over 2 root n. Applying the power rule, because root n can be written as n to the 1/2. When we differentiate, we get 1/2 n to the power of negative 1/2. Divided by, and what's the derivative of 2 to the n? Well, the derivative of a to the x exponential function is going to be itself a to the x times log of the base. So we get 2 to the n times log of 2. If we simplify this, we're going to get limit as n goes to infinity of 1 divided by root n times 2 to the n log 2. Now this limit is just going to be 0 because the numerator is just 1, is a constant, and the denominator grows very rapidly because it's a product of a root function and an exponential function. So the limit as n goes to infinity of 1 divided by root n times 2 to the n times log 2 is equal to 0. So by L'Hopital's rule, by L'Hopital's rule, the limit as n goes to infinity of 2 root n divided by 2 to the n is equal to 0. So now we can compute the limit of an as n goes to infinity. Recall that an is 1 plus negative 1 to the n, all in brackets, times root n, divided by 2 to the n, and we prove that when n is even, minus 1 to the power of n is plus 1, so the upper bound becomes 2 root n. Let me write it here so I can apply a limit to it. There's some space there. 2 root n divided by 2 to the n, and larger or equal to 0, because when n is an odd integer, 1 plus negative 1 to the n will be 0. And that forms the lower bound. The lower bound is 0. The upper bound is 2 root n divided by 2 to the n. So let's take the limit of every term as n goes to infinity. The limit of 0 as n goes to infinity is clearly 0. And we proved using L'Hopital's law that the limit n goes to infinity of 2 root n divided by 2 to the power of n, this limit is 0 by L'Hopital's rule. So by squeeze law, the limit of an is going to be 0. But always label this, always give the reason why this is going to 0, and it's because of the squeeze law. All right, so by squeeze law, we have proven that an is equal to 1 plus negative 1 to the n times root n divided by 2 to the n. This sequence converges and has a converging limit of 0. So it's always important to say the limit for which it converges. Just saying that the sequence converges is not enough. We have to give the limit to which it converges. So converges to 0. All right, let's look at another example. Here we have Bn is equal to log of sine of 1 over n plus log of n for n larger or equal to 1. Let's rewrite this using the property of logs. The property of logs, of course, is log. One of the properties is log x plus log y is equal to log of xy. So we have Bn is equal to log of n times sine of 1 over n, applying the property, the multiplicative property of logs. Now we can rewrite this using algebra. Bn is equal to log of sine of 1 over n divided by 1 over n. Now let's take the limit as n goes to infinity of both sides. So limit of Bn is equal to limit as n goes to infinity of log of sine of 1 over n divided by 1 over n. Now let's bring the limit inside the log function, so we get log of the limit as n goes to infinity of sine of 1 over n divided by 1 over n. Now notice we have the 0 over 0 pattern inside the log brackets. So you can see that the limit as n goes to infinity of sine 1 over n divided by 1 over n this has the 0 over 0 pattern. Why is that? Because 1 over n, that approaches 0 as n goes to infinity. Sine of 0 is 0, so the numerator becomes 0. And the denominator, 1 over n, approaches 0 as n goes to infinity. So we have 0 over 0 pattern. That means we have to apply L'Hopital's rule. So let's formalize the justification for applying L'Hopital's rule. So notice that we can bring the limit inside. So sine of limit as n goes to infinity of 1 over n. Taking the limit of 1 over n as n goes to infinity, that's 0. So we get sine of 0 is equal to 0. So the numerator becomes 0 as n goes to infinity. Now take the limit of the denominator as n goes to infinity of 1 over n. That, of course, is 0 as well. So we have 0 over 0 inside the brackets. We need to apply L'Hopital's rule to the limit inside the log brackets. All right. So we have limit n goes to infinity of sine of 1 over n divided by 1 over n. Applying L'Hopital's rule, we get limit n goes to infinity. Differentiate the top, derivative of sine is cosine, so we get cosine. Keep the inside intact. Now multiply by derivative of the inside. So think of it as 1 over x. Derivative of 1 over x is negative 1 over x squared. So derivative of 1 over n is negative 1 over n squared. And differentiating the bottom, derivative of 1 over n, again, is negative 1 over n squared. And negative 1 over n squared cancels from the numerator and denominator. So we get limit as n goes to infinity of sine of 1 over n divided by 1 over n is equal to limit as n goes to infinity of cosine of 1 over n. Now, taking the limit as n goes to infinity, we get cosine. So let's bring the limit inside the cosine function. Cosine of limit as n goes to infinity of 1 over n. 1 over infinity is, of course, 0. We get cos of 0, and cos of 0 is equal to 1. Now apply log to it. Because we looked at the limit inside the brackets, we have to log that limit. So limit as n goes to infinity of log of sine 1 over n divided by 1 over n, and we found the limit inside the log function using L'Hopital's rule, so we get log of 1, and that's equal to 0. So that tells us that the sequence Bn is equal to log of sine of 1 over n divided by 1 over n converges. This sequence converges, and its converging limit is 0. Converges to 0. In both examples, we used L'Hopital's rule to prove that the sequence converged. And in both cases, I guess these sequences converge to 0. All right. Thank you.